This lesson will focus on the Class B single-engine performance requirements for the landing stage of flight. There is actually only one regulation requirement for landing a single-engined Class B aeroplane. This requirement is that the landing distance must not exceed the landing distance available. In other words, the aeroplane must be able to land within the length of the runway. In order to comply with this regulation, certain points must be taken into account. These will all be discussed in this lesson. As with other regulations we have dealt with in this course, the requirements relevant to the landing of single-engined Class B aeroplanes can be found in CAP 698. JAR OPS 1 states that an operator must ensure that the landing mass of the aeroplane for the estimated time of arrival allows a full stop landing from 50 feet above the threshold within 70% of the landing distance available at the destination aerodrome and at any alternate aerodrome. This means that the aeroplane must be able to land within 70% of the landing distance available. To help clarify this, let us work through an example. If the landing distance available at the destination airfield is 2,200 feet long, then obviously the aeroplane must be able to land within 70% of 2,200 feet. To calculate this, we must divide 2,200 feet by a factor of 1.43. Carrying out this simple calculation gives us an answer of 1,538 feet. 1,538 feet is 70% of 2,200 feet. Therefore, the aeroplane must be able to achieve a full stop landing within 1,538 feet. There is another way to look at the landing requirement. If the landing distance of the aeroplane is calculated to be 1,200 feet, what is the minimum length of the landing distance available which will allow a pilot to comply with the 70% rule? In this case, we simply multiply 1,200 feet by 1.43. This gives us an answer of 1,716 feet. Therefore, the landing distance available must be at least 1,716 feet long. If the destination aerodrome has a runway with a landing distance available in excess of 1,716 feet, the aeroplane will be able to land within 70% of the landing distance available, and therefore satisfy the regulation requirement. The 70% landing regulation helps us to see the difference between net and gross performance. Here, the gross performance is 1,200 feet, but the net performance, which is always worse than the gross performance and is the 1 in a million worst case scenario, is 1,716 feet. The landing regulation we have just been discussing can be found in CAP 698 in Section 2 at the top of page 9. The regulation states that the landing distance from a screen height of 50 feet must not exceed 70% of the landing distance available. If the aeroplane cannot come to a full stop within this length, then the landing distance must be reduced, either by selecting a higher flap setting or simply by reducing the mass of the aeroplane. Having discussed the regulation requirements detailing the maximum landing distance that must be available at a destination airfield or alternate airfield, we will now examine in detail the regulations governing how the landing distance is calculated given non-standard conditions. In CAP 698 Section 2, at the top of page 9 under point B, we read that if the runway is of grass up to 20 centimeters high, the landing distance should be multiplied by a factor of 1.15. This would effectively increase the landing distance by 15%. Point C states that if there is an indication that the runway may be wet at the estimated time of arrival, the landing distance should be multiplied by a factor of 1.15. Again, multiplying the calculated landing distance by a factor of 1.15 will increase the landing distance by 15%. Point D states the landing distance should be increased by 5% for each 1% downslope. This means that for a 1% downslope, the landing distance should be multiplied by a factor of 1.05. Therefore, for a 2% downslope, the factor would be 1.1. Point D also states that no allowance is permitted for upslope. The reason for this is that upslope will reduce the landing distance. If a pilot were to ignore the reduction in the landing distance, then a margin of safety would be incorporated into the landing distance calculation. Lastly, point E states that there must be compliance with the dispatch rules for scheduled or planned landing calculations, and that these can be found in JAR OPS 1.550, paragraph C. The dispatch rules found in JAR OPS 1.550, paragraph C, state that for dispatching an aeroplane, it must be assumed that firstly, the aeroplane will land on the most favourable runway at the destination airfield in still air, and secondly, that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction. If this second assumption cannot be met, the aeroplane may be dispatched only if an alternate aerodrome is designated where full compliance of the regulatory dispatch requirements can be met. These dispatch regulations may sound a little complicated, so let's examine them further. The first assumption is that the aeroplane will land on the most favourable runway in still air or zero wind. This means that assuming zero wind at the destination airfield, the runway which would accommodate the largest possible landing mass would be selected, since that is the most favourable runway. In our example on screen, assuming zero wind, runway 04 and runway 22 both allow a maximum landing mass of 1,500 kilograms, but runway 31 and runway 13, being much shorter runways, allow a maximum landing mass of only 1,000 kilograms. Therefore, the most favourable runway in still air is either runway 04 or 22, which both allow a maximum landing mass of 1,500 kilograms. The second dispatch assumption is that the aeroplane will actually land on the most likely runway to be assigned, considering the probable wind speed and direction. In this case, runway 04 has a strong headwind for the landing, which will allow the aeroplane to land at a much greater mass than if there were no wind. In our example, the headwind has increased the maximum landing mass to 1,750 kilograms. However, runway 22 has a tailwind, which will decrease the maximum landing mass to 800 kilograms. Runway 31 and runway 13 both have a full crosswind. Therefore, the maximum landing mass for these two runways will be the same as for still air. If the second dispatch assumption is that the aeroplane will land on the runway most likely to be assigned considering the probable wind speed and direction, then it would have to be runway 04 with a maximum landing mass of 1,750 kilograms. In summary then, the first assumption requires that the pilot select runway 04 or 22 for a maximum still air landing mass of 1,500 kilograms. And the second assumption will require the pilot to select runway 04 for a maximum landing mass of 1,750 kilograms. Now we need to consider what to use as the dispatch mass of the aeroplane. If the aeroplane was dispatched at 1,750 kilograms mass, and then on arrival at the airfield the wind was less than the forecast wind, the aeroplane would not be able to land. Therefore, the aeroplane must be dispatched with a mass of 1,500 kilograms. Dispatching the aeroplane with this mass would mean that no matter what wind conditions prevail at the destination airfield, the aeroplane will have a mass which will allow it to land at the airfield. The way to simplify the dispatch rule is always consider the greatest mass in still air and the greatest mass in the forecast wind conditions, and of the two take the lesser mass as the dispatch mass. Of the two, it is the still air mass that is usually the lesser mass, as shown in our example. The exception is when there is a tailwind on a unidirectional runway. A unidirectional runway is a runway whose direction for takeoff and landing is fixed in one direction, and in this case the maximum landing mass in the tailwind will be less than the maximum landing mass in still air.